The t-distribution. The t-distribution is like a normal distribution, but with bigger tails, and it accommodates more variability in our measure of interest. So here we have a depiction of what a t-distribution looks like, and what a normal distribution looks like. And the idea, as the text says here, accommodates more variability in our measure of interest, and it's particularly good for smaller samples. Smaller samples, and also for the quantitative variable, as we have been talking about. That's what we're going to analyze: quantitative. So the procedures and the assumptions are generally the same, except the t-distribution will change based on your degrees of freedom, essentially your sample size. So it's useful because it considers the sample size, and also applies to when we have smaller samples, which means by smaller, we usually mean less than 30. So often we have samples much greater than 30. So that's good. It might not make a difference if you use a t or a normal distribution, but now we're going to be talking about the t distribution. And the whole process works the same as with the normal distribution, except that it's a little bit different in the background. That is, it's changed by degree of freedom, essentially. T-distribution is better for smaller sample size and when working with mean values, and it makes them more accurate when using the sample data as substitute for population data. Once again, as usually, as always, what we're trying to do here with these processes is that we have sample data, but we want to make a difference inference for the population. So the t-test, the rationale for the t-test is that helps with that, because it changes based on the sample size a little bit, so we can account for the sample size in our statistical tests. So let's compare here a little bit to really get this idea of the difference between the t-distribution and a normal distribution. So in the normal distribution, let's remember, these are standard deviations. This is the mean, and then standard deviations from the mean. And this here is the frequency of the occurrences. So within one standard deviation, you can find 68% of all of the occurrences of the observations in a normal distribution. So that's just the fact of the normal distribution. 34% above the mean and 34% below the mean. Within two standard deviations, we find 95% of the data, about 95.4. So 13.6 to one side and 13.6 to another side. So, and what does this all mean? Well, this means that within two standard deviations, both negative and positive, with a normal distribution, 95 observations are going to fall within that. 95% of observations are going to fall within two standard deviations. And the other question, standard deviation of what? Of whatever we're measuring. Of whatever we measure, right? As we're saying, this can be mercury in fish. And that's the beauty of it. It's general enough that it can apply. Heights of people, whatever we're measuring over here, and then the frequency of it. So suppose we have a normal distribution like heights. There's an average height, and average height may be, let's say 5'10". And within, so let's say 5'10", and then within two standard deviations would be, maybe 5'12", and then 5'8". I'm just making this up. But let's say that each standard deviation then is really 1 inch. So two standard deviations, 2 inches. So if we have a normal distribution, which we know we do when we're comparing heights, at least for particular populations, and maybe for humans in general. So we can say that 95% of all the people in the sample, in the population, are between 5'8" and 5'12". That's the area under this curve here. The area under this curve gives us the amount of frequency and the percent of units, and then also in a way the probability, because 95% of the people are between 5'8" and 5'12", then therefore I can say with 95% confidence that any one person that you pick is going to be between 5'8" and 5'12". That's the whole idea too of confidence and the probability and the frequency as well, all kind of coming together here. Now you may say, well, what is the chance of getting a person that is 5'12" from this distribution? If you just pick a person randomly, what is the chance of picking a person that is 5'12"? Well, 5'12" is over here on this side. This is 5'12", right? We just said it. So all of these people here, all of these, there could be how many people that are 5'12"? Well, or 5'12" or above, rather, not just 5'12". 5'12" or above. 5'12" just as 1 point. It's a little bit more tricky, but because we're talking about the area under the curve. So what is the chance of getting a person that is 5'12" or above? Well, 5'12" or above is going to be this area over here, this whole area over here. And we know that 95% of people, 95 plus 2, so we have to do it like this, 95.4. 95 is from here to here. 95 plus 2.1 plus 0.1 plus 2.1 plus 0.1 equals 0.6797. So from a distribution of all the people, the population of people, finding a person that is 5'12" and above, the chance is actually 1 minus 97.6%, or 97.6, which or 100 minus 97.6, it's really 1 minus 0.976, which is equal 0.024. So there's a 2.4% chance, and we could just sum these two numbers here, 2.2 rather, 2.2. There's about a 2.2% chance of getting a person that is 5'12" or above from this distribution. And likewise, there's a 97.6% chance of, did I measure something wrong here? 97, I don't know why, but anyways, might be not counting a lot of tiny details. So there's a 97.6% chance of getting a person that is less than 5'12", and there's a 2.2% chance of getting a person that is above 5'12". So that's the understanding how the normal distribution works. And then the t-distribution is virtually the same, except the curve changes a little bit, and then the calculation changes based on the degrees of freedom, the sample size. And we don't have to learn that, but as long as you understand the concept of area under the curve and the frequency of observational units, standard deviations from the mean, and so on, it's just the same general idea, except within two standard deviations, we're going to have, instead of only having 95%, we're going to have maybe 94 or 93. Now it depends with the degrees of freedom, because it changes, has the parameter, it has changes based on the degrees of freedom. But that's the kind of change that is happening on the t-distribution compared to the normal distribution. I hope this is kind of clear, and we will do more examples with the t-distribution here, and it's we can always just think about it as a kind of normal distribution that changes based on the degrees of freedom. So T distribution is centered at 0, and it changes shapes based on the degrees of freedom, and degrees of freedom is n, the sample size minus 1. We always leave 1 out just for kind of error. So it's based on the sample size, and the T distribution becomes more like the normal distribution when it was approaching 30. So I'm trying to understand here the area under the curve and the probability and chance. Let's look into this here. What is the probability of getting a value of negative 0.1, negative 2.1 or below it in the T distribution? And that's negative 0.1, negative 2.1 what? Negative 2.1 standard deviation. So this is the standardized measure here. So we can use a function, a PT function, in order to find the probability under the T distribution. And what we need to is add the measure of standard deviations here and the degrees of freedom. And so at about negative 2.1 standard deviations, there is a chance of 0.025, so 2.5%, which is, this is 2.5%. So what does this mean? Just as with the example before, this means that 2.5% of all the units of the observational units of the sample is going to be less than minus 2.1 standard deviations. And also on the other side, there's a 2.5% chance that the values are minus 2.1 or less of the T distribution. So there's a 2.5% chance, which is the area under the curve, 2.5% chance that the values in the T distribution where degrees of freedom equals 18 is less or equal to negative 2.1. So we'll also then use real examples where we're not just using generic standard deviations here and with the actual mean, and hopefully this will help clarify this concept. Before that though, let's take a look at something that happens here when we have this code over here. What does the following code do? So we're using the same function, this PT function, which is find the probability under the T distribution. And what we input is the standard deviation and then degrees of freedom. Or we can say they may call this the T cutoff point, or you can think of it the standard deviation in this case here. The level of the standard deviation, at the level of the standard deviation perhaps. So suppose it's at minus 3 and 3. So if we want to know if something is either below a value and above a value, we do what is called this two-sided test. Two-sided test, not one-sided, it's two-sided test. That is, we're checking to see what's the chance of the probability being way below that value or way above that value of concern. The thing is, with this function, it doesn't do that. It doesn't give you like this two-sided value. So what you have to do is multiply it by 2. Whatever value that you get and multiply it by 2. So you give it 1 just for the, and it defaults to the negative. It's kind of weird because it defaults to the negative. So if you put in the positive, you actually have to, you might need to minus, subtract it from 1. So you put, what's the probability of T when you have minus 3 and degrees of freedom 2? 0.0955, which is 95% chance. So this is 9.5% or 0.095. So there's a 9.5% Oh, I'm sorry. This is already calculated. It's the number looked a little bit too high. So this is already multiplied by 2. So it's going to be 4.75% chance, or 0.0475. So there is a 4.75% chance that the values in the t distribution with degrees of freedom 2 equals a -3 or below. And then we, because it's symmetrical, we can then just do the same for the other two, 4.75%. And that's why we put this 2 here, because it doesn't give us the two-tailed calculation. And then so we multiply 4.75% times 2, and then we get 9.55%. I'm approximating. Okay, and then we'll continue talking about this concept as well in the following context with some more specific examples. So I'll see you next time.